Hi, I'm Durga. I'm a postdoc in Power Performance and AX Script and AMCR. Today, I'm presenting my work on accelerating spatial queries using GPU recursive architectures. This work is part of my PhD thesis from Purdue University. Did you search for coffee near you today? You probably didn't. We have coffee outside. But if you ever search for coffee or something similar on Google Maps or any location-based services, then you're running a spatial query. Spatial queries are ubiquitous. For example, in disaster management, where you want to find people in certain danger zones, or in urban planning, where you want to designate zones based on population density. So what exactly is a spatial query? So I'm going to talk about two particular spatial queries, range query and point and polygon query. An example of range query would be, let's say you want to search for coffee near your home before trying to work, and then you look at your calendar, and then you're like, oh no, I don't have time. I can only search for coffee near work, have coffee at work later. So then you would search for coffee in a different region. So basically, the polygonal region in which you're searching is the query. And in point and polygon query, a use case would be, let's say, in case of disaster, you have some designated zones, and people are moving across zones, and you want to locate people in a given zone at a given time. So in point and polygon query, the people are they use their locations or the points or the queries. So in both of these queries, we index the static data so that when the data is queried, it's faster to retrieve it. Traditionally, the data is indexed. Spatial data is indexed using trees. Let's say you have this bunch of black points representing coffee shops or something similar. The way you would index these points is that you would first group the closest points and then put them in a box, and then iteratively group these boxes until there's one big box left. So let's say you want to run this query. You start the traversal at the root of the tree and then keep exploring the tree, down the tree, as long as the red query intersects with the node in the tree, and eventually the bottom nodes, the leaf nodes, would be the answer to your query. Let's say you want to speed up the spatial query execution even further, let's say using a GPU, but the challenge is that the spatial queries are hard to parallelize on GPU because the tree traversals and spatial query executions are irregular, which results in a poor memory request calculation, meaning it will be difficult to group the memory requests of different threads. Let's say in this tree at the bottom, a group of threads start the traversal of the roots, but they keep choosing different paths, and the thread group splits further and further as they traverse further down the tree, and eventually end up accessing very different parts of the memory. And if we cannot group this memory request into a single request, then we would be making multiple round trips to the memory, which will increase the overall runtime of spatial query execution. Traditionally, the GPUs only had shared cores, which are built for regular data structures like matrices, where the data access patterns are predictable. And this has been the case until the ray tracing cores were introduced into GPUs since 2018. So the GPU ray tracing architecture, it consists of both shader cores and ray tracing cores. And the whole architecture is designed to speed up tree traversals in the case of a particular rendering algorithm called ray tracing. So let's say you have a bunch of objects that you want to render onto the image. The way this algorithm works is that it would shoot several rays from the camera per pixel in the image plane. And when these rays go hit the objects, based on what objects the rays hit, the particular pixel is rendered. And to determine which ray is hitting which object, the objects are indexed and queried using a tree. But the tricky part is that you can use this hardware to accelerate tree traversals only if you're doing a ray tracing process. So if you want to leverage this hardware for any other application, we need to come up with an efficient mapping of our target application to the ray tracing problem. And we came up with several such mappings to accelerate spatial queries. The first is S-ray grid for accelerating range queries. recall that coffee example where we are indexing points of the coffee shops and we are querying for spatial ranges of the polygons. Another restriction with the ray tracing architecture is that it will only allow you to index three-dimensional or two-dimensional objects, but points have no space. So we choose a parameter alpha and place the points in boxes of side length alpha and let the architecture build a tree on these boxes. And then to start the threads, we need to launch some rays. So we convert the grid. So we convert the spatial range, the polygon, into a grid. Where two grid points are at most at a distance of alpha from each other. Then we shoot small rays of very small length. And when these rays go hit some boxes, it means the center of the box, the points are inside the polygon. And then for point and polygon queries, we have two methods, S-ray triangulate and S-ray proxy. Here we are indexing the polygons and we are querying the spatial points. So in S-ray triangulate method, we are basically breaking down the polygon into triangles and indexing the triangles. And then we launch point rays from the actual spatial points. And when these rays go hit the triangle, it means the point is inside the polygon. And then in the S-ray proxy method, what we're doing is we're building proxy triangles. So another restriction with the ray tracing architecture is that if the ray and the triangle are coplanar, then the hardware will not detect the intersection. And in the real world, the polygons could be three-dimensional. So what we do is along each edge of the polygon, we build a proxy triangle that goes in and out of the plane, where the edge of the polygon is the median of the triangle. And we shoot long rays. And when these rays go hit the triangle, it means the point is inside the polygon. And now for evaluation, so in this plot, on the x-axis, we have data sets where the number of polygons are ranging from 5 to 2 million, and the number of points are 100,000. They're sampled from the same geographical space as the data set. And on the y-axis, we have the runtime in the log of milliseconds. The gray bars are all different baselines, and the slashed part is the query, and the solid part is the build time. So out of all of these baselines, the S-ray grid, it's faster when the number of polygons is greater than the number of points, and it outperforms the fastest baseline by 9x speed up. So we ran several other scenarios, several other experiments. So basically, when your data is static, so when your points are static and the polygons are also static, meaning you can build index on either points or polygons. When you can build index on either points or the polygons, and the number of points is in the same order of number of polygons, then you would use the S-ray triangulate method. And when the number of points is less than the number of polygons, you'd want to use the S-ray grid method. And then in the scenario where the points are static and the polygons are the queries, and if you're ever querying more than once, meaning if you ever have to build the index on the points more than once, then you should definitely use S-ray grid, because there's no other implementation that can index points except S-ray grid. All the other baselines, they index the polygons. So if you're ever using an application where the query time is very important, for example, looking for a nearest emergency hospital or something like that, and you definitely want to use the S-ray methods. So for future work, we're interested in partitioning the input into several trees so that we could launch the trees in parallel. We could launch the threads in parallel on several trees. And then we're also interested in extending our support to other spatial queries, including polylines.